The following scenario is hypothetical and presented for educational and entertainment purposes. Imagine a single moment in deep prehistory quietly failing to happen. No lightning-struck tree gathered by curious hands, no cautious circle of stones, no first night where humans sat beside controlled flame and realized the dark no longer owned them. Imagine that moment simply never occurring. At first glance, it seems like a small absence. After all, humans existed for hundreds of thousands of years before mastering fire. But in science, tiny missing variables can reshape entire systems. Remove gravity from a solar system and planets scatter. Remove fire from human evolution and civilization begins to drift into a completely different orbit. In our known timeline, control of fire appears somewhere between 400,000 and 1 million years ago. The evidence lies in charred bones, hearth structures, and chemical traces in ancient soil. Once fire entered human life, it triggered a cascade of biological and cultural changes. Cooked food released more calories. Pathogens were destroyed by heat. Nighttime extended into usable hours. Predators began to fear the glowing perimeter of camps. But imagine a parallel world where this cascade never begins. Lightning still ignites forests, of course. Wildfires still rage across grasslands. Early humans still observe flames from a distance, just as wolves watch thunderstorms from hilltops. Yet, observation does not become mastery. No one discovers how to carry embers. No one learns how to preserve a spark overnight. Each blaze appears and disappears like a temporary miracle. Anthropologists in this alternate timeline would eventually notice something strange in the fossil record. Human jaws remain larger than expected. In our reality, cooking softened food and gradually reshaped the human skull. Teeth shrank, digestive systems shortened, and brain size increased because less metabolic energy was spent processing raw plants and meat. Without cooking, that shift never occurs so quickly. Raw tubers remain tough, meat stays fibrous. The human body must invest more biological energy into digestion. That energy must come from somewhere. And in evolutionary economics, energy spent on digestion cannot be spent on brain growth. The result is subtle but profound. Intelligence still rises because social cooperation still favors it, but the growth curve slows. Brain expansion that took hundreds of thousands of years in our timeline now stretches across millions. Night remains another unsolved barrier. Without firelight, darkness still belongs to predators. Lions, hyenas, and saber-toothed cats patrol the African savanna after sunset. Early humans retreat into trees, rocky shelters, or tight clusters for protection. Cultural exchange, stories, teaching, tool-making remains confined to daylight hours. Anthropologists call this the darkness ceiling. In our world, fire broke that ceiling open. In this alternate world, it remains firmly sealed. But the most dramatic consequence appears in a place few people expect: disease. Heat sterilization, even in primitive forms, kills parasites. Cooked meat reduces exposure to dangerous microbes. Smoke repels insects. Fire-hardened tools enable better butchery and sanitation. Remove fire and pathogens become permanent companions. Parasitic infections remain common. Raw meat spreads bacteria. Drinking water cannot be boiled. Early medicine never gains its first accidental laboratory, the cooking hearth. The human lifespan in this world rarely crosses 30 years. Not because humans are weak, because microbes are undefeated. Still, evolution never stops experimenting. Humans adapt in unusual ways. Teeth become tougher, stomachs grow more acidic. Cultural survival strategies develop around fermentation, drying in sunlight, and stone-based food processing. But one limitation refuses to disappear. Metal never arrives, because every metal technology, copper, bronze, iron, begins with controlled heat. And without fire, the entire metallic age of humanity remains locked inside the Earth's crust. Which means that thousands of years later, when humans finally begin forming the first cities, they do so in a world still trapped in the Stone Age. But the strangest consequence has not appeared yet. Because in this parallel Earth, When the first scientists finally begin studying energy, they will face a terrifying realization. Humanity has spent nearly 2 million years surviving without understanding the single force that powered our entire civilization in the real world. And when they finally try to control it, they will be attempting the most dangerous experiment in the history of their species. For nearly 2 million years in this alternate Earth, humanity lives inside a strange technological paradox. They are clever, observant, cooperative. They build shelters, carve intricate stone tools, map the stars, and learn the behavior of animals with astonishing precision. But one invisible wall holds them back from crossing the threshold into civilization as we know it. Temperature. In our timeline, temperature became humanity's first controllable physical variable the moment fire was mastered. With heat, matter becomes flexible. Wood bends, clay hardens, ore transforms into metal. Heat is the gateway that allows humans to reshape the physical world rather than merely adapt to it. But in this world, heat remains untouchable. Clay pots never appear because pottery requires kilns. Metal tools never exist because ore must be smelted. Even something as simple as hardened bricks remains impossible without sustained high temperatures. Architecture therefore evolves along a completely different path. Instead of cities of fired brick and stone, settlements grow using dense biological materials: compressed mud, woven fibers, resin-hardened wood, and natural stone. The result is something that archaeologists in our timeline would find both beautiful and unsettling: cities that look alive. Entire neighborhoods are built from massive tree frameworks grown deliberately over decades. Walls are formed from living roots guided through stone molds. Resin extracted from certain plants hardens in sunlight and acts like a primitive cement. Instead of chimneys and furnaces, buildings rely on airflow tunnels and reflective mineral surfaces to regulate temperature. It is a civilization shaped not by flame, but by biology. Yet even this adaptation cannot escape the medical barrier created by the absence of fire. Without sterilization by heat, surgery remains primitive and extremely dangerous. Infections spread easily. Bone fractures often become fatal. Parasites remain a constant burden across all human populations. Early healers learned to rely heavily on herbal chemistry instead of physical intervention. Plants become the laboratories of this world. Over thousands of years, human societies begin cultivating enormous botanical knowledge. Entire forests are turned into living pharmacies. Some plants are bred to produce stronger antimicrobial compounds. Others are used to ferment crude alcohol-based disinfectants. In a strange twist of evolutionary pressure, this world becomes vastly more advanced in plant chemistry than our own. But even plant chemistry cannot solve everything. The real breakthrough arrives unexpectedly during a geological disaster. Somewhere along a volcanic ridge, perhaps in East Africa or Indonesia, an eruption exposes something humanity has never before encountered up close: naturally burning gas vents. These vents ignite when lightning strikes them, producing flames that can burn continuously for years. At first, people fear them. In a world where fire has never been domesticated, a stable flame looks supernatural. Stories spread of earth spirits that breathe light. Entire communities avoid the glowing hillsides where the ground burns without wood. But eventually, curiosity overcomes fear. Scholars, by now a respected class in many societies, begin documenting the strange phenomenon. They notice patterns. The flame persists because invisible gas escapes from underground. When the gas flows, the flame survives. When the gas stops, the flame dies. For the first time in human history, flame is no longer a random event. It becomes an observable system. And that realization leads to the first major scientific crisis of this alternate civilization. Because if flame is a natural process governed by rules, then perhaps humans could control it. But control will not come easily. Generations of scholars debate the danger. Many argue that flame is inherently destructive and unpredictable. They point to volcanic disasters and lightning fires as proof that humanity has survived precisely because it never tried to command such forces. Others disagree. They argue that understanding flame could unlock entire fields of knowledge: medicine, materials, energy. For decades, the debate divides entire nations until one experiment changes everything. A young natural philosopher decides to test whether the burning gas from the volcanic vents can be transported through hollow stone channels. The idea seems simple, but if it works, it would mean something humanity has never achieved before: a flame that can be summoned at will. And the moment that flame appears, inside a laboratory carved from volcanic rock, human history will split into two eras: the age without fire, and whatever terrifying age comes after. The first controlled flame in this world does not appear in a warm cave surrounded by curious hunters. It appears inside a laboratory. By the time this moment arrives, humanity has already built vast settlements grown from wood, stone, and living structures. Scholars catalog plants the way our world cataloged metals. Medicine is dominated by fermentation, molds, and plant-derived antimicrobials. Astronomy is sophisticated. Mathematics exists. Writing systems span continents. But one domain of physics remains almost completely unexplored: high-temperature reactions. When the young natural philosopher channels volcanic gas through hollow basalt tubes and sparks it inside a sealed chamber, the result is not merely a flame, it is a scientific shockwave. Because for the first time, humans observe a controllable heat source that can exceed anything found in nature outside volcanoes. At first, the flame is terrifying. Witnesses describe it like a living creature. The flame roars from the gas outlet, bright blue and violently hot. Unlike wildfires, which consume visible fuel, this fire seems to feed on nothing but invisible air from the stone pipes. Scholars immediately begin measuring its effects. Clay placed near the flame hardens within minutes. Sand begins to soften and slump into glass-like droplets. Animal bones left in the chamber turn brittle white. For researchers trained in biological chemistry, these transformations seem almost magical, but science has a way of accelerating once the first variable becomes controllable. Within a few years, laboratories across several cities begin building their own gas-fed flame chambers. Engineers refine the piping systems. Regulators are carved from layered stone valves that control gas pressure. Suddenly, heat becomes something that can be dialed up or down. Humanity has accidentally invented the first furnace, and the consequences arrive faster than anyone expects. The first breakthrough occurs in materials. A group of experimenters notice that certain greenish stones placed in the furnace release small droplets of shining metal. The metal is soft and bright, unlike any mineral previously seen in nature. At first, they believe it to be some form of liquid rock. It is copper. In our timeline, the Copper Age emerged thousands of years after fire was already commonplace. But in this world, the discovery hits a civilization that already possesses advanced mathematics, organized research institutions, and long-distance knowledge networks. So instead of centuries of slow experimentation, metallurgy explodes into existence almost overnight. Within a single generation, copper tools begin appearing everywhere: needles, surgical blades, precision carving instruments, mechanical components for irrigation systems. The difference between stone and metal is so dramatic that entire industries transform within decades. But the most dramatic change appears in medicine. Copper blades can be sterilized by flame. For the first time in history, surgeons discover that wounds treated with heated tools become infected less often. It takes time for scholars to understand why, but the evidence becomes overwhelming. Heat destroys invisible disease agents. The medical revolution begins immediately. Boiled water becomes standard practice in hospitals. Instruments are passed through flame before procedures. Mortality rates begin dropping across entire populations. Life expectancy climbs higher than 30 years, then 40, then 50. Humanity begins living long enough to accumulate knowledge across multiple generations, and with longer lives comes a surge in intellectual progress. But the greatest discovery of all happens almost by accident. One night, While testing furnace temperatures, an apprentice places a piece of transparent glass between the flame and a measuring instrument. The glass cracks, distorts, and suddenly focuses the flame's light into an intensely bright point on the stone table. The apprentice notices something strange. The focused light is hot. Very hot. Soon researchers realize that heat does not only come from fire, it can also come from concentrated sunlight. Mirrors and lenses can direct energy in ways no one previously imagined. In other words, humanity begins discovering energy itself as a universal concept. What started as an attempt to control flame now expands into the study of thermodynamics, optics, and chemical reactions. Within 2 centuries, technologies emerged that in our timeline required thousands of years of gradual development. Steam power appears astonishingly quickly once metalworking exists. Glass lenses lead to microscopes and telescopes. Scholars finally see the microbes that plagued their ancestors for millennia. Humanity, once trapped in the biological limits of the Stone Age, suddenly leaps forward. But there is a dark twist hidden inside this technological explosion. Because the civilization discovering fire is not primitive, it is already scientifically organized. It already understands experimentation, and it already possesses complex political systems capable of funding massive research projects. Which means that the moment humans master high-temperature chemistry, they do not stop at copper. They push immediately towards something far more dangerous, something that in our timeline took thousands of years of gradual technological buildup to reach. In this world, it will arrive in less than 3 centuries. The Age of Fire has begun, and humanity is about to discover the most destructive reaction ever unlocked by heat. For most of human history in this alternate world, the absence of fire acted like a natural brake on technological acceleration. Civilization grew slowly, carefully through biology, observation, and plant chemistry. Knowledge accumulated in libraries grown from living wood and carved stone. Scholars debated theories for decades before attempting dangerous experiments. But once controlled flame appears, the brake disappears. The furnace does not merely introduce heat, it introduces rapid experimentation. Within a few generations, laboratories transform into something resembling modern research institutes. Teams of natural philosophers begin cataloging every mineral they can obtain. Each stone is crushed, heated, melted, and observed. Strange vapors emerge from some ores. Others change color when exposed to air. Metals combine with unfamiliar properties. The scientific culture of this world, already highly organized before the discovery of fire, moves with astonishing speed. Copper becomes bronze. Bronze becomes iron. In our world, the Bronze Age lasted thousands of years. In this timeline, metallurgy advances so quickly that entire eras collapse into a few centuries. Cities that were once grown from living trees now rise in structures supported by iron frameworks. Water systems improve. Agriculture becomes more productive. Transportation expands across continents. Humanity begins to look familiar. But something else emerges alongside this rapid progress. Energy hunger. Every furnace consumes gas from underground reservoirs. Cities begin drilling deeper into the earth to capture more of the invisible fuel feeding their flames. Mines expand. Gas channels stretch for miles beneath the surface. Eventually, engineers face a problem. Natural gas vents cannot supply enough fuel to power the growing number of furnaces, engines, and industrial processes. Scholars begin searching for other sources of energy. And this is where the alternate path of human history becomes truly strange. In our timeline, fire led first to wood, then coal, then oil. The entire Industrial Revolution rested on burning fossil fuels. But this civilization skipped wood burning entirely. Instead, their earliest understanding of flame came from geological gas. So their research focuses immediately on underground chemistry rather than forests. Geologists begin studying rock formations that trap combustible gases. Chemists analyze the gases themselves, methane, hydrogen, carbon compounds, They discover that certain reactions release enormous amounts of heat without requiring traditional fuels. One discovery in particular changes everything. Hydrogen. A group of researchers studying water electrolysis, separating water into its component gases, realized something shocking. When hydrogen gas combines with oxygen, the reaction releases an explosive burst of energy, much more energy than simple burning. At first, hydrogen reactions are used for industrial heating. Furnaces fueled by hydrogen burn hotter than anything humanity has ever controlled. New alloys appear, glass production improves, scientific instruments become more precise, but scientists quickly notice another property. Hydrogen reactions produce only water, no smoke, no soot, no toxic residue. In other words, the world's first large-scale energy system becomes clean combustion. Cities powered by hydrogen engines produce almost no pollution. The sky above industrial centers remains blue. Rivers stay relatively uncontaminated. This civilization accidentally bypasses the environmental devastation that defined our own industrial revolution. For a brief moment, the future looks astonishingly bright. Human lifespans climb above 70 years. Medical science flourishes once heat sterilization becomes universal. Telescopes map the planets. Microscopes reveal the cellular structure of life. Electrical experiments begin spreading through universities. Humanity appears to be approaching a golden age. Then the second major scientific climax arrives. It begins with the study of minerals used in high-temperature furnaces. Certain heavy rocks behave strangely under intense heat. They emit faint, invisible radiation that slowly darkens photographic plates. Physicists become fascinated. What begins as curiosity about unusual rocks turns into a deeper investigation of atomic structure. Scholars realize that matter is composed of smaller building blocks, atoms, and that some atoms contain extraordinary amounts of hidden energy. The discovery is electrifying. If atomic bonds can release energy when rearranged chemically, what happens when the nucleus of an atom changes? Theoretical calculations suggest something terrifying. Nuclear reactions could release millions of times more energy than ordinary combustion. In our timeline, humanity discovered nuclear physics after centuries of industrial development, global conflict, and massive military infrastructure. By the time nuclear weapons appeared, the world was already politically unstable. In this alternate world, the situation is very different. This civilization discovered fire only recently. Its scientific institutions are cooperative rather than militarized. International research networks share knowledge openly across continents, which means the discovery of nuclear energy does not begin as a weapon program. It begins as a dream of limitless energy, reactors that could power entire continents without fuel shortages, desalination plants turning oceans into fresh water, spacecraft engines capable of leaving Earth's gravity. But as physicists assemble the first experimental reactors, they realize something that chills the entire scientific community. The energy locked inside atoms is not merely powerful, it is unstable. One miscalculation could release enough heat to vaporize entire cities. And for the first time since the moment humans ignited that laboratory flame centuries earlier, the same question returns to haunt their civilization. Was mastering fire the beginning of human progress, or the moment humanity finally gained the power to destroy itself?